Okay, so what's going to be our first step? Is this big enough? Can you guys see it? Bigger. Ice table. Okay. Okay.
Are we back?
Yeah, we're back. Can you hear us?
Yeah.
Okay, good. We may crash again, just so you know. It's been one of those days. But we'll keep going until we can't go anymore. Or until I throw the computer out the window, one or the other. Okay, so we're going to calculate Kc with the initial concentration of 0.0150 molar of ammonia and 0.0150 molar of oxygen with an equilibrium concentration of N2 equal to 1.96 times 10 to the minus 3. So what do I know? Okay, so we have the initial for the reactants. So we have 0.0150 molar and 0.015 molar. Zero and 0. Okay. And then what else do we know? Okay, so we know the equilibrium concentration for N2, right? Which is 1.96 times 10 to the minus 3. Okay. So what are we going to need to do to calculate our Kc? So what do we know it's going to happen? Okay. Okay, so how would I set that up in this case? These are going to be negative x. Okay. So now remember, we have to take into consideration the molar properties of each one, right? Yeah, so we could say 4x. So then this guy would be 3x. And then these guys are going to be 2x and 6x. No, but you have to take the mole to mole ratio. You could set it up in terms of, because it's all relative, right? So if we set it up as this being x, right? We could say that this is x. If we say that this is x, then we know that this guy is going to be, let's see, 4. So then that'll be 2x, right? Because it'll be the molar ratio between it, right? So it's a relative type of thing. So by us setting it up this way, we're saying, well, whatever x is. So we could make it so that this here is x, right? But then we just have to adjust all of the molar ratios based upon that, right? So if we had done the same thing over here, then that means that this guy would be 2 halves, right? I mean, not 2 halves, 3, sorry, 3 over 2, yes. And then this guy would be 3, right? Does that make sense? Because we have to take into consideration the molar ratio. Okay. Okay, so if we set it up in this fashion, and we have that 2x, is equal to 1.96 times 10 to the -3. Then we know what x is, right? And then what would be this number at equilibrium? It would be what? Would it be equal to x at equilibrium? That's right. It would be my initial concentration minus the 4x. This one was going to be, because you have that look right now, right? And so this is the initial, right? At the starting point, we have that much. The change is how much we're going to be removing, and then that's going to give us our equilibrium, right? So whatever we're losing here, we have to subtract from there. So all of this is being produced to produce our products at that equilibrium concentration, okay? So that's the reason why we have to subtract it by 4x, right? Here, this guy is going to be the same thing, but now it's 3x because that mole-to-mole ratio, right? So it's going to be see if I can move some things around a little bit. There's a little more room. Okay. And then we know that this guy is just going to be 6x, right? Okay, so let's go ahead and solve for x. So we get x equal to 9.80. Okay, so then the water is going to have at equilibrium 6 times that value. Concentration of water is going to be 6 times that value. Okay. 5.88 times 10 to the -3. The concentration of oxygen at equilibrium is going to be so 3 times that value, or 1.1. 0.00150 minus 3 times 9.8 to the negative 4. And that's going to equal 1.21 times 10 to the minus 2. Molar. Concentration of ammonia. It's going to equal this value times 4. So it's 0.015 minus 4 minus 4 times 9.80 times 10 to the minus 4. Oops. 0.0111 molar. Okay. So then my Kc is going to equal. So what's going to be the expression for my Kc? N2 squared H2O to the 6th power over ammonia. Okay. Okay, so then we plug in our numbers. So we have for nitrogen 1.96 times 10 to the minus 3. And that's going to be squared times water, which is 5.88 times 10 to the minus 3. And that's going to be to the 6th power. Divided by the ammonia, which is 0.0. Okay, you said 1.11 times 10 to the negative what? Times 10 to the negative 2. And that's to the 4th power. And then we have the oxygen, which is 1.21 times 10 to the 2nd power. And that's going to be cubed. Sorry to make everything run into each other. Okay. Questions? Okay. So, see what we get. So think about these problems, they're so tedious. Right? Okay, so the nitric acid is going to be in there. So check the solutions for the ammonium thiosulfate, and then also check the solutions for the potassium thiocyanate. Thiocyanate. Yeah. So, and you know what I mean by the solution.
Yeah.
And it should be in order if we have it.
Okay.
And if we don't have it, then we'll just do the ones that we can do. Okay. Yeah. Yeah. It's in there. Okay. And then so they'll need the spectrometer. So let me show you where that's at. You guys are doing the calculations for me? What was that? Okay. Give me 1 second. Okay. Or week, yeah, exactly. Okay, you have that look. It's everywhere, I know. Bear with me. Okay, so since we have our values, do you mind if I erase this part to kind of give us a little more room to work? Okay, so then I'll drag everything down here so it'll make a little more sense. Okay. Okay. Second power. Okay, so let's go ahead and do the math. So I like doing it simple, so we're going to do each one independently, and then we'll get some answers that way. Okay, so we have 1.96 e to the negative third power, and it's going to the second being squared. So then that gives me 3.84 times 10 to the 2, 4, 6, 10 to the minus 6 power. Okay, 5.88 to the negative third power. And then we're going to take that to the sixth power. So we get times 4.13 times 10 to the negative 14. Divided by 1.11 to the second power, to the, I'm sorry, minus 2 power. And that's going to be to the fourth power. So then we get 1.51 times 10 to the 2, 4, 6, 8 to the minus 8 power. And then we're going to have 1.21 to the minus 2. And that's going to be to the third power. So it's going to be cubed. So we get 1.77 times 10 to the minus 6. Okay, so to make our lives a little bit easier, it's going to cancel out. That's going to cancel out. That's 10 to the minus 6 or 10 to the minus 6. So then we'll have, let's go this here, and then that's going to just leave me to the minus 6. So we have 3.84 times 4.13 divided by 1.51. So then I get Kc equals 1.05 times 10 to the minus 5. Is that what you got? Uh-huh. Ten to the 6, negative 6. But you got 5.90. Okay, let me try it again. What did you get? $1.96 to the third power. It's negative third power, sorry, negative third power. And then, so then that is going to be squared, right? Oops. Negative 3, and then that's going to be squared. So you get, that's going to be 3.84 times 10 to the minus 6. That's 2, 4, 6, yep. Okay, so then we get 5.88 e to the negative 3. And that is going to be to the 6th power. So I get 4.13 times 10 to the negative 14. For this, for the 5 point, yeah. Okay. And then I have 1.11 to the negative 2 power. And then that is going to be to the 4th power. So I get 2, 4, 6, 8. So I get 1.5, that should be 1.52. You get the same using my numbers? Okay, so I may have miscalculated. And then 1.21 e to negative 2. And that's to the 3rd power, right? And so that's 1.77 times 10 to the 2, 4, 6. Okay, so then using those numbers, so if I have 3.84 e to the negative 6, 8, 4, 6 times 4.13 e 3.84 times 4.13 e to negative 14. Okay, divided by 1.52 e to the negative 8 divided by 1.77 e to the negative 6. Two, 4, 6. Times 10 to the power of negative 18. So I got 5.89 times 10 to the negative 6. Yeah. Yeah, so it's your exponent. So if it was 10 to the minus 18. So if you do these numbers, so 3.8, so type in 3.84 times 4.16. Yeah, that's 10 to the negative 6. Yeah. No, it's 14. Negative 14, yeah. Yep. Okay. Yeah. Okay. Cool. It just takes us a while to get there. Okay. Can I clear? Okay, so let's see. Using the following equation, so use the following equation with an equilibrium constant of Kp equal to 0.110 to calculate the partial pressure of ammonia at equilibrium if 55.0 grams of ammonia hydrogen sulfide is placed in a 5.00 liter container. Yes, you should do the ice table because you do have a initial concentration. So, but the key is that we have a initial concentration, right? But what is the rule about the initial? What was that? I'm keeping my mouth shut until nothing. It was just I'm gonna let you guys figure out. So we gonna do an ice table, you said? So first thing that we're gonna do is do an ice table, right? So we have ice, ICE. Okay. So our initial concentration. So let's kind of take a step back. What is going to be our expression, our equilibrium expression? Kp is going to equal what? Okay, so are you guys sure? So it's the partial pressure of H to S and the partial pressure of ammonia and you said over the reactant. Is there something about the reactant that we need to pay attention to? It's a solid. So what does that mean? What was that? That's right. It's not going to mess with the equilibrium as long as we have something there, right? Okay, so that basically means that we have X and X, because that's going to be the change, right? X and X here is going to equal our equilibrium constant, our Kp, right? So then we're going to have Kp is going to equal X squared, right? So then Kp is just going to be 0.110 equal to X squared. So then Kp is equal, each P, partial pressure of each one is going to be just the square root of that. Are we good? What are we missing? We're missing 3? Okay. They picked them up.
But we've got anything else with the phase 1 sulfate, the ammonium sulfate, the FeCl3 over there, and the citric acid, and
Okay.
that's it.
Okay. That sounds great. And all they're doing is taking the spectrometry, spectrometer wavelength, spectrometer, measure the. Okay, so which one? So they can't do which one of these? So they can do this one. They can't do this one. They can do this one.
Yes. Yeah.
They can do this one.
Yes.
But they can't
can
do
do
this
that
one. Okay, so let's get to that. Okay, so just 2 of them.
Yeah.
Yeah, sure, or this one as well.
No, we found it.
Okay. All right.
There we go.
Okay.
So,
Okay.
it's just that one. And
Okay. And we do have this one as
we
well.
do have that one.
Okay. So that's not too bad. 2 out of yeah, and I believe I have this one at Fireball. Unfortunately, that's one. I bet that's what they can't do. But that's added into the reaction, right? So wait a minute, hold on. So that's 2, 1. So technically they can't do any of the experiments because they all have to be added into the.
Yeah. Oh, yeah.
Yeah.
Oh.
Okay, questions, concerns? Cash, too late? Credit cards?
Save money, gift card.
Okay, got two more slides. Jesus. Okay, write the net ionic equation for the reaction of iron 3 nitrate with potassium thiocyanate to form thiocyano iron 3 complex ion. Calculate the equilibrium concentrations for the reactions and the products with a Kc 1.10 times 10 to the third. Dilute the concentration of 0.0200 molar iron 3 nitrate and diluted concentration of 0.00 molar iron 3 nitrate and 0.100 molar potassium thiocyanate. Okay, so first off, we need to figure out what the hell the reaction is, what's going on with this reaction, right? Okay, so we got Fe is reacting with, FeNO3 subscript 3, okay, is reacting with SCN. What was that? Don't panic. There's nothing to panic. No, it's what this is the experiment that we should be doing, right? Do me a favor, send me an email and to add those chemicals to the list. So it has been an incredible week this week. The ones that were missing, the 3 that were missing, or the four that were missing. Because all the other ones are liquid, are they aqueous solutions? So we probably need the powders. Did you also take a look at the very bottom? The ones that were pulled out? Yeah. Okay. But that's for the solution. But I'm saying at the very bottom of the dry chemicals, because remember we had to pull a lot of them out because they're old and we need to replace them. Yeah. So those, did we take a look at those, or did you guys take a look at the database? Okay, yeah, because the database is correct. Yeah. And so, and they were not in the database. Okay, I thought I ordered them. Yeah, yeah. Okay. Okay, and what are our products? What are we going to end up with? Sorry, 50 million things. So we're going to end up with the thiocyanyl iron complex ion. So we're going to end up with okay. Actually, it would be 2. Because it's a complex ion, so the thiocyano is going to have a -1 charge. This here is going to be a +3 charge. And the fact that it's thiocyano, there's only one of those added to it. So it's not going to be 3 components of it. Yeah. So the potassium and the nitrate, they exist. Yeah. They're going to form potassium nitrate. And let's see, so it's going to be a 1-to-1 ratio. And then the fact that they said that this is an ion complex, that lets us know that it doesn't neutralize it still has a charge associated with it. You understand? What was that? Yeah, you can balance it. It should balance out perfectly. Except for we need 3 of these, right? Yes, 3 of these. And then we'll need, so that's 3. So then this guy will be 3. To neutralize it completely, but it's a, yeah, but it doesn't neutralize completely. It's forming an ion complex. So in other words, it's still going to have a charge associated with it, right? So yeah. So we're going to end up with 2 SC and minus left. Potassium thiocyanate, iron. What was that? Oh, that's good. You both got jury duty this year? That's weird. So if we do the net ionic equation, these guys are going to cancel each other out. This is just going to be plus, and then this guy is just going to be so then the only thing that we're going to have left is this, right? Okay, so now since we know that molar wise, right, we have for every one iron 3 nitrate, we have 1 iron 3 ion. Okay, so it says, so with the KC on this equation, so this would be our net ionic equation, and then the calculate the equilibrium concentration of the reactants and the products with the Kc and diluted concentrations of, okay, so then that means that if we're starting out with our initial concentration of this is going to be 0.0200 molar. And then our initial starting concentration of this guy is going to be 0.100 molar. And this is going to be 0 initially. So then this guy is going to be, what will be the change? This is I, this is C, this is E. The change would be what? Negative X, negative X, and X. Okay, so then we get 0.0200 minus X, 0.100 minus X, and then this guy's going to be X. Oh, yeah. I'm sorry, I got excited about something real quick. Okay. I just had a great idea. So then we have Kc is going to be equal to 1.10 times 10 to the third power. And that's going to be equal to X divided by 0.0200 minus X times 0.100 minus X. I gotta stand up. Okay, so what can we assume? What's the assumption we're going to make? 5% rule. Okay, so we're going to make the 5% rule. Okay, so if we make the 5% rule, we can neglect this and we can neglect that. So then we get Kc is going to equal, it's not looking good though. That's my guess, 1.10 times 10 to the third times X divided by 0, oops. That's going to equal X divided by 0.002. And 0, 0. Okay. So then if we solve for X, we have X is going to equal 1.100 times 0.002. X equals 2.2. Right. So X equals 2.2. So we know that that can't be the case, right? So what does that mean? We got to do it the long way. Oh, yes, we got to do it the long way. Okay, so let's do it the long way. Do you mind if I erase this stuff down here since we already established our ice table? Okay. Okay. So then we'll get 0.0200 minus x times 0.100 minus x times 1.10 times 10 to the third. So I'm just taking this equation here and multiplying. Okay, so then if I do the math, let's see, distribution rule, if I remember correctly. So this guy times this guy, and this guy times this guy, and this guy times this guy. And this guy times this guy. Okay. So I get x squared. Actually, let me fix this. Let me do it right. Do you mind if I erase this part over here? So I have 1.10 times 10 to the third times x squared. I get x times x, that's x squared. Or minus x times minus x is x squared. Minus 0.120x plus 0.002. Shift it over a little bit, yeah, to see. Thank you. No, it's fine. I was going to shift it over anyway, but I wanted to finish writing it, so then I need to figure out how much room I had. And then we know that that's going to equal x, right? So I need to shift over some more. Or actually, we'll do this. Hold on. How about that? Does that work out a little better? Okay. Poor Abel. He already started drinking already. He's not even of age yet. Okay, so then we go ahead and multiply this with everything. So we get 1.10 times 10 to the third power times x squared minus, I have to plug it in. My brain's not working today, so I can't do it in my head. 1.10 times. So then that's minus 1.32 times 10 to the second x plus 1.10. Yep, we're going to have to do the quadratic, yes. 2.2 and then equals x. So then we end up with 1.10 times 10 to the third x squared minus 1.33 times 10 to the second power x plus 2.2 equals 0. Did I screw up? Yeah, that's 10 to the second power. What was that? For which one? Oh, yeah. So it's 133. Yeah. 133. Yeah. 132. Yeah. Well, initially up here it's 132, but then you have to bring this out over, right? So now it's 133. Yeah. Okay, so we got to plug into the quadratic. You guys remember the quadratic formula? Oh, I'm glad you guys remember because I don't. So you said it's negative b square root of the square root of 4 AC. What was that? Oh, b squared. Okay. Plus or minus the square root of 4AC divided by okay. So we plug in our values. Am I forgetting something? Yes. What was that? Negative b. Okay, hold on. Go, you're gonna have to go slower now because my brain is not working today. So you said it's negative b plus or minus the square root b squared plus or minus is just a plus. Okay. 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 Minus b plus or minus the square. Okay. You guys are sure about that? Okay. Okay, good. Okay, I just want to be sure. Like I said, I could calculate. I could actually figure it out, but it'll take me a minute. So the brain's not working today. So let's go ahead and plug in those values. So we get b is, so that would be 133. So negative b would be, do this, negative. So like I said, brain's not working. Plus or minus square root of 133 squared minus 4 times 1.1 to the third power. Oops, put 1 times 10 to the third power times 2.2 divided by 2a, or 2 times 1.10 times 10 to the third power. Okay, so let's see, 133 squared minus 4 times e to the third power times 2.2 equals divided by 2 divided by 1 point e to the third power. Take the square root of that. So we'll get 133 plus or minus 1 point. Still does not work out right. 1 plus or minus. B. Let's try this. 33. 33. Oh, when you say you have two answers because it's plus or minus, right? Okay, good. Okay, what was the answers that you guys got? Okay, you said 0.101. Okay. 0.10. Okay. 0.0198. 198. Okay, so it's been a long day. I know you. I've just been to one day. Okay, 0.0198. Okay. So we had 0.101. Right? So let's talk about that. So is it possible for us to have 0.101 molar of our product? Why isn't it possible? Tell me. That would be what, okay. What did you guys get? Negative? No. Okay, wait. So let me write down the numbers here, right? And then I'm gonna erase all of this. Can I erase all this to kind of make it a little bit, to kind of prove a point here? So we'll erase this part here. It has been a long day today. My throat. Yes, they still should be open right now. Are you there, Abel? We didn't lose you. Sorry.
Yeah, I'm here.
Okay, so we had two values, right? So you said, I'm going to see how much I can butcher it this time. 0.0198 molar. Okay, and then you also had 0.101 molar. Okay, so now, why can't it be this value? Is there a reason? Yeah, you calculated that for X. Okay, that's exactly it. So one thing, it's greater than the thiocyanate. We also know that one of these guys are in excess, right? If it's a 1-to-1 ratio, right? So this is 1x, so 1 to 1 to 1, right? All of these are going to be 1-to-1 ratios, right? So this is our smallest value, right? This value here is much bigger than our smallest value. So we know that that wouldn't be possible, right? You guys remember limiting reagents? So this guy would be limiting. This guy would be in excess. And so as a result, it couldn't be more than our limiting reagent. Right? Does that make sense? So we want to pay attention to those values. So you can't get more than what you started off with, right? Okay. Our last problem, and then we'll call it a night. You guys are getting out of the lab because we don't have the chemical. I apologize. We may have been able to do one, but I took I took it to NDC because they're in the middle of doing the experiment, and I forgot to bring it back. I just want to cry some days. You know, this is one of those days. Okay, so we have phosphorus pentachloride gas decomposing into phosphorus trichloride and chlorine gas. Write the chemical equation, write the reaction quotient for this reaction at 600.0 Kelvin. The equilibrium constant Kp is 11.5. Calculate the pressure of the phosphorus pentachloride if 2.50 grams of gas is placed into 0.50 liters container, assuming it's an ideal gas. Calculate the partial pressure for each of the reactants and products when equilibrium has been reached. Okay, what are we going to do? What was that? Write the chemical equation. Okay. So, phosphorus pentachloride gas. What does that look like?
PCl5.
PCl5. And it's a gas plus, oh, sorry, it decomposes to what is it decomposing to? PCl3. And Cl2. And I'm joking, what else? Okay, now what's next? Okay, so it will be an ice table. Okay. So initially, what are we starting off with? Forgot to change it into what? Thank you. Moles. We have to change it to moles. So we have 2.450 grams of PCl5. Okay, so what is the molar mass of PCl? So phosphorus is it's 30 what? So 31. Okay. And Cl, if I remember correctly, is what? 35.45 times 5. So altogether, it's going to be 208. Check my math. 0.25. Okay. So we're going to end up with 0.01176 moles. True? False? Okay. Okay, so now we got the number of moles. And it says, assuming that it's an ideal gas. What does that tell me? What was that? Ideal gas law. What is the ideal gas law? PV equals nRT. Somebody tattooed it on themselves, didn't they? Okay, so we want the pressure, right? So then we know that pressure is going to be P equals nRT divided by V. So then we get number of moles, which is 0.01176. And then R, which is 0.0821. I'm going to have to move it because I'm running out of room. And T, we know is going to be 600 degrees Kelvin. And V is going to be half a liter. Okay, so we get pressure is going to be equal to So what did you guys get for pressure? Okay, so that's going to be our, what is that going to be? That's going to be our initial, right? So we're starting off with 1.16 ATM. Okay, how much of the PCl3 are we starting off with? 0, 0. Okay. Okay, the change. Then X. Okay. Because you're losing something, right? And if you're losing, where's it going? To the products, right? And remember, we're talking about moles. And so we're looking at moles. And so it's important that we make sure that we do the right mole ratio, right? So in this case, it's 1 to 1, right? Okay. Yeah, because literally this guy's being split up into this component and that component. So, okay. So then this number here is the equilibrium. At equilibrium, it's going to be what? Minus X. Then we know that this guy is just going to be X. This is going to be X. Okay. So then our equilibrium expression is going to be Kp PCl2 times PCl2, PCl3, sorry. That's really a P. Divided by PCl5. Okay. So then we plug in our values. So we get Kp equals X squared over 1.16 minus X. And that's going to equal 11.5. So if we assume the 5% rule, what am I going to do? So we'll just get Kp equals X squared over 1.16 equals 11.5. So we get x squared equals 11.5 times 1.16. So we get x squared equals 13.384. And so x is going to equal 3.65. Okay, so 3.65 ATM. Okay, I have a question. Is that going to be, it's not 5%. So that means that we have to do it the log way, right? So, which isn't horrible. So we'll go back to the original equation. So write it over here, Kp equals x squared over 1.16 minus x, which equals 11.5. So we get x squared equals 11.5 times 1.16 minus x. So we'll get x squared equals 13.34 minus 11.5 times x. So then I get x squared minus, I'm sorry, it should be plus 11.5 x minus 13.34. And that equals 0. Okay, so we do the quadratic formula. Do you mind if I erase this up here? So we have b plus or minus, oh no, yeah, b plus or minus the square root of b squared minus 4ac over 2a. There you go. It's right here. Okay. So if we plug in our value, we get minus 11.5 plus or minus the square root of 11.5 squared. I'm going to actually move this down. I don't know to where. I'm going to erase this down here. 11.5 squared minus 4 times negative 13.34. I'm running out of room. Over 2. Squared square root Okay. What did you guys get? $1.06. Okay, so we know we can't have a negative, right? So okay. Questions? Concerns? Cash? Kool-Aid? Credit cards? You'll take a credit card? You should take cash. Don't worry about credit. Credit card means you have to pay a bill. Or go to bankruptcy court, exactly. Oh, man. It's not on the table here. Okay, so we're gonna stop today here.